Hi guys, today's topic is about SVM support vector machine, and this is really well known and well performing classifier. So for example, if there is these two kinds of data, then we just want to find some hyperplane which can separate these two data points, and which will have a maximum margin. This gap is called margin here. So this algorithm is just to find some hyperparameter of weight and bias. So if this hyperplane have this weight and bias, then we are trying to find the best weight and bias which maximize this margin, this distance. Alright, so I'm going to derivate about SVM with some math, but it will be really simple. So in classification, alright, because it will be a linear classifier, so I will write it like this, and if it is larger than 1, then we call this target is +1, and in the other hand, if it is less than -1, then our target will be -1. That means it will classify as blue or it will classify as red point. And as I explained, we are choosing weight and bias such that D is equal to 1 over weight or omega. So our goal is to find hyperplane with maximal margin. We always try to find something to maximize or something to minimize because it is the way to develop and improve our algorithm. So I can say minimize weight because it will be same, right? Because it will be 1 over W. So in our basic math, I can write it down. Arg mean of this, it will be our goal, but there is a constraint. Here from these two equations, if we multiply Tn for both sides, then it can represent in this equation. It is kind of easy way and make it simple because these two lines become one line, but it involves two because if Tn target or classification class is -1, then it will be same as this equation, right? So it can be again written as Lagrangian formulation. And this Lagrangian formulation is really helpful when there is something to mean some quadratic equation to minimize with linear constraints. So this is linear constraint, and this is quadratic equation to minimize. So it can apply Lagrangian formulation. The equation will be rewritten as it is Lagrangian equation, and we call this is Lagrange multiplier. Again, if for those who Lagrangian formulation is first, so you can easily understand. We just put our original cost or loss function, our objective function, and it can combine, this Lagrangian equation can combine and include the constraints into our equation. And here we have Lagrange multiplier. So this one equation can represent our objective function with our constraint. So one equation can involve these two. If you need more insight about Lagrange multiplier, there is some more YouTube video, and it will be really helpful to understand better. So let me just make some simple example to use Lagrange multiplier. If there is some circle in the plane or in the space anywhere, but I will just assume this circle on the plane, and if there is some line, we can draw, let's say we can draw any lines like this or this or this or whatever. But if we want to then let's say we have a given line constraints, and we are looking for we have one point. We want to find the minimum radius, because it will be r squared and it's kind of similar in terms of math equation. Then you know that when it is just touch this line, when they just meet only one single point, then it will be the optimum case. So in this case, we can also apply this Lagrange equation and the formula of this circle into this quadratic equation, and this linear constraint can be applied to here. And then what we have to do is we differentiate with our variable. Then okay, let me try first. Then Lagrange L around derivative with regard to b, and let's find the point which will be the 0. Then because b only we have this term and this term, right? Therefore it will be 0. And something more about, let's differentiate with regard to omega. Then so here it will be firstly omega and minus omega. Okay, we have these three terms, with this sigma. So is equal to 0. Then let me just make it simple. It can be written as like this. See? So if this condition and this condition meet, then it can be the optimal point for this situation. Okay? Because it is the definition of Lagrange multiplier. But here's one problem. Lagrange formulation can be applied when it is just equal sign. When it is only equal sign, it is done with this case. But since it is inequality sign, then we have some more things we have to consider. That is KKT. It is Karush, Kun, Tucker. So it can apply, it can explain, let's say, if it is inequality sign, this equation should meet this condition as well, then we can apply all the theories regarding Lagrange formulation. So in this case, let me just simply explain. If some function is like f something to quadratic, some quadratic equation, anything, and plus lambda and our function which is constraint, then lambda should be equal or same, equal or larger than 0, and and function should meet this condition. Then it is important, lambda multiply fx should be 0. So if lambda is larger than 0, then fx should be 0. If lambda is 0, then fx, the function, should be larger than 0. So if these three conditions meet, then we can still apply this equation. So in our case, importantly, and Lagrange multiplier should be equal or larger than 0 on our constraint function. This one should be equal or larger than 0. Therefore, it can be written as like this. Okay. So this equation, you can see this, actually yn is same with wtxn plus p. Okay, so it is same with this equation. It is same with this equation. Okay. So since we already calculated these two equations, therefore these two equations can apply to here. So this w can be substituted to here. Okay, so I will apply this and make the equation simpler. Then it will be So here, because t1 square will be 1, because t and target will be +1 or -1, so t square will be always 1, so I will multiply t both sides. Then I can rewritten b as n minus sigma alright, but because it is unstable, we normally find support vector by finding mean value, average value. So I think you guys are confused about these parts. Why I'm calculating this? Because here we have this S. It is support vector. So as I said, if Lagrangian multiplier, let's say if Lagrangian multiplier is not 0, then it means this one should be 0, right? Vice versa. If an is 0, then tn yxn minus 1 is not 0. It is really important concept in support vector immersion, because if it is 0, that means let's see, this is our hyperplane and this is our margin, and let's say we have this point and many points outside, and we have this point and other points really far outside. So this equation is explaining this. So this plane, hyperplane. So this only support vector, the points which lies on this boundary will be called as support vector. This is support vector. So if Lagrange multiplier is not 0, then they will be support vector. So on the other hand, if they are not laid on the support at this boundary, then Lagrange multiplier will be 0. So this kind of point which is not laid on this boundary will have Lagrange multiplier as 0. So they are not used in constraint term. Alright, so here we can just calculate the points on the support vectors for calculating hyperplane like B or W later. Okay, so it is really computationally helpful because we just need to use and calculate this support vector, which is really few points compared to the whole data points. Okay, so it seems really happy to just use support vector because it requires only few data points, which means not much computational effort. But here still we have a problem, because if our data point has let's say m dimension, then it will when we calculate this Lagrangian formulation, it requires a lot of computational efforts with regard to our dimensions, cubic. So if it has a really high dimensions, then it will fall into curse of dimensionality. So we have some solution. We can apply dual formulation. So the point is that I will rewrite the equation. Here, before we had a Lagrange equation with multipliers. Let me just rewrite it because it will be much more helpful to understand. This equation can be rewritten as dual form. This Lagrange form is called primer form, but it will be written as dual form, and the meaning or like the intuition of applying this dual form is we just change our variable and we just change the way of expression of the way of expressing the equation by changing the variables. So but we are still dealing with the same problems, but because we change the variables, so if it is primer form equation, let's just assume it, but primer form equation will cover like some other area, but the best point, the optimal point is same for this equation and this equation. So dual form can be helpful sometimes. So first of all, let me just introduce how to convert primer form into dual form. Then it will be much better to understand. So let me try. And right before we calculated that W and B is some equation. When we derivate this equation with W, then we could calculate because we have this term and this term will be the opposite. We already calculated. If you are not sure, then I can for sure to show this equation and this equation. Alright? B and B can be rewritten, not rewritten, just be written as like this, and 10 is 0. Okay? Okay. So because we know this W, I will put this value here. Then this equation can be written as word I just expand this equation like this, and firstly we can say this is all right, this is 0, so we're happy because we have less term, and it can be rewritten as like this. And also I will put this value not only for this W and also for this W, and we'll make this equation simpler. Then it will be alright. I changed it. I can say this is dual form. We changed our prima form into dual form. It is same equation but with different variables because it contains W and B, but we don't have W and B anymore, so it is the equation with regard to this Lagrange multipliers. So maximize Lagrange multiplier and also Lagrange equation under constraints. Multipliers equal or larger than 0 for all n, and still we have this constraint from here. So, and also hyperplane W will be light on this support vector. It represents the number of support vectors. Okay. So that means we have only, let's say we have n variable. Actually ns variables. Then, and this, for these equations, our computation effort is proportional to the number of data points. This is the point, but our number of points is not whole data points, only for this support vector. Therefore, because we have not much support vectors, it seems like really a high computational effort, but our computational effort does not rely on the number of dimensions. So it is really helpful if the dimension is really high, right? And even in practice, we only need to calculate between from to this one to here. This is thanks to quadratic solvers. So in summary, dual form or dual problem is good for high dimension. High dimension problem. Even in case of dual problem, we can apply corner trick. My lecture is going really long, so I will explain more about corner trick, and will explain more about select cases, which all the data points cannot be separated like this. If like we have this range of points, then there is no such line which we can 100% perfectly separate. So we will use this slack concept, but it does not go too much from these fundamentals. So thank you for watching today's video.